The planetary core consists of the innermost layer of a planet, which may be composed of solid and liquid layers. Cores of specific planets may be entirely solid or entirely liquid. In the Solar System, core size can range from about 20% to 85% of a planet's radius. Gas giants also have cores, though the composition of these are still a matter of debate and range in possible composition from traditional stony iron to isotope fluid metallic hydrogen. Gas giant cores are proportionally much smaller than those of terrestrial planets, though theirs can be considerably larger than the Earth's. Nevertheless, Jupiter has 10 to 30 times heavier than Earth, and exoplanet HD 149026b has a core 67 times the mass of the Earth. Discovery. In 1798, Henry Cavendish calculated the average density of the Earth to be 5.48 times the density of water. This led to the accepted belief that the Earth was much denser in its interior. Following the discovery of iron meteorites, Wickert in 1898 postulated that the Earth had a similar bulk composition to iron meteorites, but the iron had settled to the interior of the Earth, and later represented this by integrating the bulk density of the Earth with the missing iron and nickel as a core. The first detection of Earth's core occurred in 1906 by Richard Dickson Oldham upon discovery of the P-wave shadow zone, the liquid outer core. By 1936, seismologists had determined the size of the overall core as well as the boundary between the fluid outer core and the solid inner core. Formation. Accretion. Planetary systems form from a flattened disk of dust and gas that accrete rapidly into planetesimals around 10 kilometers in diameter. From here, gravity takes over to produce Moon-to-Mars-sized planetary embryos, and these develop into planetary bodies over an additional 10 to 100 million years. Jupiter and Saturn most likely formed around previously existing rocky and/or icy bodies, rendering these previous primordial planets into gas giant cores. This is the planetary core accretion model of planet formation. Differentiation. Planetary differentiation is broadly defined as the development from one thing to many things, homogeneous body to several heterogeneous components. The hafnium-182, tungsten-182 isotopic system has a half-life of 9 million years, and is approximated as an extinct system after 45 million years. Hafnium is a lithophile element and tungsten is hydrophile element. Thus, if metal segregation occurred in under 45 million years, silicate reservoirs develop positive HFW anomalies, and metal reservoirs acquire negative anomalies relative to undifferentiated chondrite material. The observed HFW ratios in iron meteorites constrain metal segregation to under 5 million years. The Earth's mantle HFW ratio places Earth's core as having segregated within 25 million years. Several factors control segregation of a metal core, including the crystallization of perovskite. Crystallization of perovskite in an early magma ocean is an oxidation process and may drive the production and extraction of iron metal from an original silicate melt. Core merging. Impacts. Impacts between planet-sized bodies in the early solar system are important aspects in the formation and growth of planets and planetary cores. Earth-Moon system. The giant impact hypothesis states that an impact between a theoretical Mars-sized planet Theia and the early Earth formed the modern Earth and Moon. During this impact, the majority of the iron from Theia and the Earth became incorporated into the Earth's core. Mars core merging between the proto-Mars and another differentiated planetoid could have been as fast as 1,000 years or as slow as 300,000 years. Chemistry. Determining primary composition. Earth. Using the chondritic reference model and combining known compositions of the crust and mantle, the unknown unknown component. The composition of the inner and outer core can be determined: 85% Fe, 5% Ni, 0.9% Cr, 0.25% Co, and all other refractory metals at very low concentration. This leaves Earth's core with a 5 to 10% weight deficit for the outer core, and a 4 to 5% weight deficit for the inner core, which is attributed to lighter elements that should be cosmically abundant and are iron-soluble (HO, Cs, P, and C). Earth's core contains half the Earth's vanadium and chromium, and may contain considerable niobium and tantalum. Earth's core is depleted in germanium and gallium. Weight deficit components: Earth. Sulfur is strongly siderophile and only moderately volatile and depleted in the silicate Earth, thus may account for 1.9 weight% of Earth's core. By similar argument, phosphorus may be present up to 0.2 weight%. Hydrogen and carbon, however, are highly volatile and thus would have been lost during early accretion and therefore can only account for 0.1 to 0.2 weight% respectively. Silicon and oxygen thus make up the remaining mass deficit of Earth's core, though the abundances of each are still a matter of controversy, revolving largely around the pressure and oxidation state of Earth's core during its formation. No geochemical evidence exists to include any radioactive elements in Earth's core. Despite this, experimental evidence has found potassium to be strongly siderophile given the temperatures associated with core formation. Thus there is potential for potassium in planetary cores of planets, and therefore potassium-40 as well. Isotopic composition: Earth. Hafnium-tungsten isotopic ratios, when compared with a chondritic reference frame, show a marked enrichment in the silicate Earth, indicating depletion in Earth's core. Iron meteorites, believed to be resultant from very early core fractionation processes, are also depleted. Niobium-tantalum isotopic ratios, when compared with a chondritic reference frame, show mild depletion in bulk silicate Earth and the Moon. Palisite meteorites. Palisites are thought to form at the core mantle boundary of an early planetesimal, although a recent hypothesis suggests that they are impact-generated mixtures of core and mantle materials. Dynamics. Dynamo theory is a proposed mechanism to explain how celestial bodies like the Earth generate magnetic fields. The presence or lack of a magnetic field can help constrain the dynamics of a planetary core. Refer to Earth's magnetic field for further details. A dynamo requires a source of thermal and/or compositional buoyancy as a driving force. Thermal buoyancy from a cooling core alone cannot drive the necessary convection as indicated by modeling. Thus, compositional buoyancy is required. On Earth, the buoyancy is derived from crystallization of the inner core. Examples of compositional buoyancy include precipitation of iron alloys onto the inner core and liquid immiscibility both, which could influence convection both positively and negatively depending on ambient temperatures and pressures associated with the host body. Other celestial bodies that exhibit magnetic fields are Mercury, Jupiter, Ganymede, and Saturn. Stability and instability. Small planetary cores may experience catastrophic energy release associated with phase changes within their cores. Ramsey, 1950, found that the total energy released by such a phase change would be on the order of 1029 joules, equivalent to the total energy release due to earthquakes through geologic time. Such an event could explain the asteroid belt. Such phase changes would only occur at specific mass-to-volume ratios, and an example of such a phase change would be the rapid formation or dissolution of a solid core component. Observed types. The following summarizes known information about the planetary cores of given non-stellar bodies. Within the Solar System, Mercury has an observed magnetic field, which is believed to be generated within its metallic core. Mercury's core occupies 85% of the planet's radius, making it the largest core relative to the size of the planet in the Solar System. This indicates that much of Mercury's surface may have been lost. Early in the Solar System's history, Mercury has a solid silicate crust and mantle overlying a solid iron sulfide outer core layer, followed by a deeper liquid core layer, and then a possible solid inner core making a third layer. Venus. The composition of Venus's core varies significantly depending on the model used to calculate it, thus constraints are required. Moon. The existence of a lunar core is still debated. However, if it does have a core, it would have formed synchronously with the Earth's own core at 45 million years post-start of the Solar System, based on hafnium-tungsten evidence and the giant impact hypothesis. Such a core may have hosted a geomagnetic dynamo early on in its history. The Earth has an observed magnetic field generated within its metallic core. The Earth has a 5 to 10% mass deficit for the entire core and a density deficit from 4 to 5% for the inner core. Ni value of the core is well constrained by chondritic meteorites. Sulfur, carbon, and phosphorus only account for 2.5% of the light element component. Mass deficit. No geochemical evidence exists for including any radioactive elements in the core. However, experimental evidence has found that potassium is strongly hydrophile when dealing with temperatures associated with core accretion, and thus potassium-40 could have provided an important source of heat contributing to the early Earth's dynamo, though in a lesser extent than on sulfur-rich Mars. The core contains half the Earth's vanadium and chromium, and may contain considerable niobium and tantalum. The core is depleted in germanium and gallium. Core mantle differentiation occurred within the first 30 million years of Earth's history. Inner core crystallization timing is still largely unresolved. Mars possibly hosted a core-generated magnetic field in the past. The dynamo ceased within 0.5 billion years of the planet's formation. HFW isotopes derived from the Martian meteorite Zagami indicate rapid accretion and core differentiation of Mars, i.e. under 10 million years. Potassium-40 could have been a major source of heat powering the early Martian dynamo. Core merging between proto-Mars and another differentiated planetoid could have been as fast as 1,000 years or as slow as 300,000 years. Impact heating of the Martian core would have resulted in stratification of the core and killed the Martian dynamo for a duration between 150 and 200 million years. Modeling done by Williams al. 2004 suggests that in order for Mars to have had a functional dynamo, the Martian core was initially hotter by 150 K than the mantle, and with a liquid core potassium-40 would have had opportunity to partition into the core, providing an additional source of heat. The model further concludes that the core of Mars is entirely liquid, as the latent heat of crystallization would have driven a longer-lasting dynamo. If the core of Mars is liquid, the lower bound for sulfur would be 5 weight %. Ganymede has an observed magnetic field generated within its metallic core. Jupiter has an observed magnetic field generated within its core, indicating some metallic substance is present. Its magnetic field is the strongest in the Solar System after the Sun's. Jupiter has a rock and/or ice core 10 to 30 30 times the mass of the Earth, and this core is likely soluble in the gas envelope above, and suprimordial in composition. Since the core still exists, the outer envelope must have originally accreted onto a previously existing planetary core. Thermal contraction evolution models support the presence of metallic hydrogen within the core in large abundances. Saturn has an observed magnetic field generated within its metallic core. Metallic hydrogen is present within the core. Saturn has a rock and or ice core 10 to 30 times the mass of the Earth, and this core is likely soluble in the gas envelope above, and therefore it is primordial in composition. Since the core still exists, the envelope must have originally accreted onto previously existing planetary cores. Thermal contraction evolution models support the presence of metallic hydrogen within the core in large abundances. Extrasolar Thernian planets. A Thernian planet results when a gas giant has its outer atmosphere stripped away by its parent star, likely due to the planet's inward migration. All that remains from the encounter is the original core. Planets derived from stellar cores and diamond planets. Carbon planets, previously stars, are formed alongside the formation of a millisecond pulsar. The first such planet discovered was 18 times the density of water and 5 times the size of Earth. Thus the planet cannot be gaseous, and must be composed of heavier elements that are also cosmically abundant like carbon and oxygen, making it likely crystalline like a diamond. PSR J1719-1438 is a 5.7 millisecond pulsar found to have a companion with a mass similar to Jupiter but a density of 23 grams per cc, suggesting that the companion is an ultra-low-mass carbon white dwarf, likely the core of an ancient star. Hot ice planets. Exoplanets with moderate densities suggest that such planets like GJ1214b and GJ436 are composed of primarily water. Internal pressures of such water worlds would result in exotic phases of water forming on the surface and within their cores.